We will now talk about the existence of the derivative. So far this class, we've looked at limits when they exist and when a function is continuous. So let's say that we have a real valued function f. Recall that we said the limit as x approaches a of our function is equal to some value L if the left-sided and right-sided limit equal the same value. And remember, we said that f of a does not need to be defined. Okay, so you can have an open hole there basically, and the limit will still exist. Now for continuity, we said that in order for a function to be continuous at a point A, f of a had to be defined, so we can have holes. We also needed the limit to exist, so in other words, the left and right-sided limit had to be equal. And not only that, but the actual value of this limit had to be what f of a is defined as. So we saw that there was a relationship between limit and continuity. Is there a relationship between continuity and differentiability? And the answer is yes, there is. And the answer is yes, there is. We have a theorem. Now, what does the theorem say? The theorem says that if we have a function, if f is differentiable, let's say at some point A, so if f is differentiable at x is equal to a, then f is continuous. At x is equal to a. Now, please note that the converse is not true. So in other words, so if f is continuous at x is equal to a, it does not necessarily imply that it's differentiable. So it does not imply that f is differentiable at x is equal to a. Okay, so if we have a jump discontinuity or a removable discontinuity or an infinite discontinuity, our function is not going to be differentiable at those points, but we can have situations, they're called corners or cusps, where the limit will exist. We'll have continuity at the corner or cusp, but we won't have differentiability. And when I say corner or cusp, what I mean by that is this first little picture here of this V, this is what we call a corner. And then for this other picture here, this is what we call a cusp. And the main difference between them is that cusps don't necessarily have straight lines like corners do, but they're basically both a type of corner. Just we use the term cusp if these lines are possibly curved. Now, how do I know that they're not differentiable? So remember that if a function is differentiable, we can draw a tangent line at a particular point. Well, what happens if we try to draw a tangent line for these corners or cusps? So say I'm coming from the left side. Okay, so if I draw a tangent line, I'll have something like this. If I'm drawing it for this cusp here, I'll have a tangent line that looks like this. But if I'm coming from the right of either one of these, notice that we have different tangent lines. So this is tangent 1. And then we have tangent 2. We get this crisscross shape. Okay, so this means that they're not differentiable. If you think about, drawing a nice smooth curve like a polynomial, if you draw the tangent line from the left or from the right, it's the same line. So we have differentiability. But for corners and cusps, we don't have that. We get this crisscross shape. Now, one famous example of a function that's continuous but not differentiable is this thing called the absolute value function. And we're going to define what it is. And then we're going to look to see if it's continuous and then differentiable. So the absolute value, in terms of notation, we use these bars, these absolute value signs, and it's defined as a piecewise function. If x is greater or equal to 0, we have that the function is x, but if x is less than 0, we have that it's negative x. And what does that function look like? Well, it looks like a v, basically. Okay, we have these straight lines. Okay, that both go to 0. So the only real problem that we have with this function is, we're going to have to check to see what's happening here at this corner. Corner at x is equal to 0. Because everywhere else we don't have a problem. This is just a line. This is just a line. These are linear functions. So we know that they are continuous and they're also differentiable. Okay, so we don't have a problem anywhere, but we are going to have to check what happens at 0. Everywhere besides 0, everything's okay. So first, let's check out continuity. So we'll go through the 3 criteria and we'll make sure that everything's met. So the first one is that f of 0 is defined. And it is defined. Okay, we don't have an open hole here. We have that it's equal to 0. Okay, so this is defined, and specifically f of 0 is equal to 0. Now, let's look at the limit if we come from the left or from the right. So if I'm coming from the left and I reach x is equal to 0, I'm at 0. If I come from the right and reach x is equal to 0, I'm still at 0. So my left and right-sided limit are equal. So the limit as x approaches 0, it exists. And what is it equal to? It's equal to 0. So the limit as x goes to 0 of f at 0 is equal to 0 because our left and right-sided limit, so 0 plus f of x, is equal to 0, but this is also equal to the limit as x goes to 0 from the left of f at x. Okay, so we know that the limit exists. And finally, the value of our limits, the limit as x goes to 0, of f at 0, or f of x rather, sorry, xx, okay. This is equal to f at 0, okay, which was equal to 0. So our absolute value function is continuous, and x is equal to 0, because all of those 3 points are satisfied. Now, let's look at differentiability by definition. Okay, so we're looking at f prime of 0, the limit as h goes to 0, the x that we're interested in is 0. Now let's write out what this is. So the limit as h goes to 0, now f at 0 plus h, so our function is absolute value. Okay, so I have absolute value of 0 plus h, and then minus, I have the absolute value, I'm interested at 0, and all of this is over h. Okay, now those zeros, okay, we don't have to write them. We have the limit as h goes to 0 of the absolute value of h over h. But what does this go to? Okay, I can't simplify it anymore. So this is going to approach the absolute value of 0 over 0. All right, but this is indeterminate form. That means that our f prime of 0, this does not exist. Okay? And then, as I said before, so if a function has a removable jump or infinite discontinuity, then your function cannot be differentiable at that point. And also, if we have corners or cusps, the function is not differentiable at that position. So hopefully that was helpful in allowing you to see the difference between continuity and differentiability.